don't think we can test properly anymore.
Okay.
Yeah. So we are testing live on stream.
Could you? Okay.
Yeah. For everybody that is watching us online, we are starting in a few minutes.
So I just, so I can speak now and be online. Okay. Good afternoon, everyone, especially the friends on site and online. Welcome to the NARS workshop at AGI 2025 here at Reykjavik University. My name is Bowen Xu, and I'll be your host for this half-day session dedicated to the Non-Axiomatic Reasoning System, or NARS. So one of the most sophisticated and ambitious approaches in AGI. NARS, as many of you know, aims to build thinking machines, systems capable of reasoning, learning, planning, and more in a unified and flexible framework. Over the years, the NARS community has grown to include researchers and engineers and students from across the globe. So today we have an exciting lineup of talks that will explore both the theoretical foundations and practical applications of NARS, as well as its connections with other cutting-edge AI technologies. So before we begin, I would like to thank our sponsor, Clever Library, whose support has helped make this year's workshop possible. And now let's get started. So our first speaker is Pei Wang from Temple University, the creator and principal architect of NARS. And in his talk, Self-Control in NARS, Pei Wang will discuss how systems' internal mechanisms, including mental operators, allow NARS to perceive itself, influence its own cognitive processes, and balance automatic and deliberate reasoning. This dual process approach mirrors aspects of human cognition, including emotions and feelings. So please welcome Pei Wang.
Hello, everyone. It's a pity I cannot be there in Reykjavik, so I will present this topic online. As you can see, it's talking about self-control in NARS, or technically, for those of you who know this basic design, we're talking about the plan to implement non-axiomatic logic level 9, which is the top level or top layer, which has not been fully implemented in the current system yet. So today, what I'm going to talk about is a detailed, kind of relatively detailed conceptual design. It's not something we have fully implemented, so we don't really have a demo, but we have some ideas to share at the workshop. So first, a very quick review about the related concepts in NARS. This is especially for the people who are not very familiar with this project. The overall architecture is kind of similar to a typical reasoning system. So first, there is an input-output channel which can accept information in several different forms. It can use NARS, which is a formal language defined for the system. And also, it can use other format which convert into NARS, or it can also directly connect to sensory motor mechanism, like to control a robot, some other things. And then all those information will be converted into NARS sentence and put into what we call an overall experience buffer. Some of them will be selected to put into memory, which is a huge conceptual graph. And then in each working cycle, some of them will be picked. Typically, a task and belief will be selected from the memory and sent into the inference engine, which implement this non-axiomatic logic. Then the result will be put into a so-called internal experience buffer. And some of them will be selectively merged with the input from the outside in this overall experience buffer, then go back to memory, which is a circle. Okay, some of the result of the inference will also be sent to the output, which will be sent to the user, other system, or to be used to control the movement of the robot and so on. Okay, so the overall architecture is relatively simple. So I already touched several key concepts. NARS is for non-axiomatic reasoning system, which is adaptive and also designed under assumption of insufficient knowledge and resource, which we have explained in many publications. And the logic part is called NAL, or non-axiomatic logic, which was designed and implemented in 9 layers. And today we are going to talk about the top layer. The layers below, from level 1 to 8, has been mostly implemented already in several different implementation, and most of them are open source. And NARS is the language which is used both for internal representation and also for external communication. And also a new concept we introduced in recent publication is so-called NARS Plus. That is you'll see in the previous diagram, everything outside NARS are optional. It's not taken to be part of the system, but you can connect it to different, say, for example, sensors and actuators in a plug and play manner. So if you take those things into consideration, then what you have is a NARS Plus, which is NARS Plus the connected devices, okay, which is used as tools or organs of the system. So that's the key concept used. And also the representation language is so-called term-oriented language. A term is identifier of a concept used in the system, which can be atomic or compound, meaning it with internal structure. We don't have the time for details, but I just want to stress one thing, that a term is not the traditional symbol in symbolic AI, because it does not refer to an existing or outside object or event to get as a meaning. Instead, its meaning is grounded in the system's experience about this term, or whatever the system know about it. Okay, that's a crucial difference. We have already several publications on it. So I'm not going to repeat the details. Then a special type of term, special, and they're actually compound term, is called a statement. Okay, the formal structure is roughly like a subject, a copuler, and a predicate, which is similar to Aristotle's logic, not similar to first-order predicate calculus. Okay, it's a special term in the sense that it can have a truth value. And also, we have a lot of publication about NARS truth value, which contains two components, two real numbers between 0 and 1. One is called frequency, another one is called confidence. Then a special type of statement is called an event, which is different from an ordinary statement in that its truth value is about a certain period of time. Especially, we can have compound events, which is event 1 followed by event 2, or event 1 and event 2 happen at the same time, roughly speaking. Then you see this is a whole hierarchy, right? Now we have, you see, a statement is a form of term, an event is a type of statement, now an operation is a type of event. Meaning that it's an event realizable by the system or can be directly executed or achieved by the system. So it's called operation, which is format is one format is operator followed by a list of arguments, just like function call or method call. And then we have another type of event, which is called a goal, which is also, you see, it's a statement or with a truth value, which is something to be achieved or to be pursued by the system or to be desired by the system. Similar to truth value, desire value is also a matter of degree. Okay, so there's something desired stronger than something else by the system. We don't have the detail for that, but I want to mention that there are two key points which make a goal different in NARS compared to the ordinary goal in most other AI systems. One is there are multiple goals in the system normally, except in very simple or at the very beginning, which itself is not new, right? But what is new is normally those goals may conflict with each other in terms of what they want as well as their requirement for resource. Another thing is the goal in NARS typically cannot be fully achieved. It's usually only partially achieved to a certain degree, okay, which make it different from the ordinary goal in AI systems, especially in symbolic AI systems. So now the system's knowledge, what we call knowledge or belief, is a statement with a truth value and a desired value. And both of them actually come from the system's experience or from the evidence in the experience, which will decide whether the system believes this is the case or whether the system wants it to be the case or not. Then we already mentioned every sentence is typically a subject and predicate, both are terms related by a copuler. In that form, it's actually very similar to Aristotle's logic. But different from it and many other logic is in NARS, there are only 4 basic copulars, okay, as listed here. All of them are actually quite often used in knowledge representation in AI. But what makes NARS different is the conceptual graph only allow those 4 relations, accurately speaking. All the other conceptual relation is converted into one of them, typically is into inheritance. One thing special about operation is we have something called a schema, which is also a term used by some similar system, which describe the precondition and consequence of each operation. But again, the difference between NARS and the similar system is each operation is typically not described by a unique or single schema. Instead, is described by multiple schemas. And also, each of them is incomplete and uncertain to a different degree. Okay, so each of them describe operations one aspect. or one possible usage. Then the procedural inference. I just mentioned several typical forms. For example, induction. NARS can derive schema and a compound term from its observation. Very simple example, if it observed event A is followed by event B, maybe something in between, then in certain situation, it will form a compound term. One is say that probably A implies B. This, of course, is true to a certain degree, especially at the very beginning if you don't have a lot of evidence. And also, it can take A followed by B as one unit. So this is a compound term. Okay. Then build on that, it will have something more and more complicated. For example, it can say that if A is followed by B, and then that implies C. Then using those things, we can do deduction, use a schema and a new observation to anticipate a consequence and also to form some plans. For example, if you see A again, if you already know that A implies B to a certain degree, then it will derive anticipation for B. Say it's kind of like I expect B to follow, but then this will be conformed or disconformed with future observation, which will lead to the revision. So sometimes if B indeed happened after A, then this A implies B will become stronger and stronger gradually. On the other hand, if A is not followed by B, and this one will become weaker and weaker, but also it's always a matter of degree. It's not completely believe or disbelieve. And also it can form plan, which typically in this case is nothing but a compound operation. Okay. So if the system say, okay, under condition of A, if I do B, then I'm going to see C. Then if under the condition of C, if I do D, I'm going to see E. And then based on this two premise, by deduction of the logic, you can say, okay, if under the condition A, if I do B followed by D, and both are operations, this special symbol is used as a prefix to indicate its operation can be executed by the system itself. And then it can get E. So in this way, the system can do plan without actually executing an operation and then to anticipate what consequence there will be, including multiple steps. The abduction can provide explanation for unanticipated or unobserved events. A simple example is if the system knows that A typically implies B, and then it observed B, and then it formed explanation, say A must have already happened, even though I haven't heard about it or I haven't observed it directly. So this is a highly simplified description about the basic rules of NARS. There are many others. So far, what I just said is basically a summary of what we have already done. Okay, we have already implemented in several different program language. Everything I have said so far. So from this moment, from this slide is the new idea. We want to add into future implementations of NARS. One is the concept of internal experience. We have already seen that in diagram, we have an internal experience buffer. Where here, the basic idea is we have a streams of mental operations. We have already mentioned the concept of operation, which is what you can think it is what a robot can do to the outside world. It can move around, it can pick up things, it can drop things, and so on. What we call mental operation is different. This is what NARS can do to itself. Here, to itself, especially we're not talking about to its body, like recharge its battery and so on. We're talking about to its mental process. Okay. It can change what it will think about to a certain degree. So that's called a mental operation. So the internal experience is a stream of mental operations. It's in a sense we can say that the system have a certain level of ability to remember what it has done in its thinking process. So that sequence forms the system's internal experience. So it have internal sensors. This sensor is not about the situation in the outside world. Instead, it's about its internal events, which we can call it the feeling. Later we'll say more details about that. And also, there are also actuators. And this actuator, again, is not like the arm or wheel of a robot, which work in the outside world. Here, actuators of mental operation means that operations which can change the system's own working process. For example, what to think about next. So compare this internal experience. This is new. Okay, the external experience was there from the very beginning of NARS. So that's where all the operations starts. But compared to that, you see the similarity is both of them actually looks very similar. They're nothing but a sequence of Narcisse sentence. The key difference is mental operator I already mentioned. They're about the system itself, and also they're built in as part of the system. External operators, on the other hand, as we have shown in the architecture, is plug in, plug and play. Okay, so NARS does not assume any concrete physical operator, like it can be used to control a robot with 4 wheels, as well as to control another robot with 2 legs. Okay, you just need to hook them to the system so that you turn a NARS into a NARS plus. But the internal mental operators are part of the system. Okay, so that's why we consider it as a layer of the logic itself. So it's built in. And also they're abstract, meaning that it directly gets the sensation at the level of conceptual description. Instead of going through electrical activity or neuron firing and so on. So they're by nature abstract. Now let's see some concrete example about what we call local operation, that is mental operation that work on specific aspects or components of the system. One group is what we call feeling, okay, which can be triggered by significant change within the system. For example, we already talked about the truth value, which can be changed by new observation. But if the change is large enough, it will trigger a feeling which will enter into the system's internal experience. So it's kind of like previously the system believed that is true, then realized it's not, it's false. Not only that happened within that experience, also the system will notice that change. It's kind of like telling itself, oh, it's a surprise, okay, what I believed was wrong. And the same thing for desire. And another thing is called priority, which is used for attention allocation. Okay, so all the major change in those things will enter the system's internal experience as a form of feeling. And also those feelings can be combined to get some perceptions about a mental situation. For example, what we call satisfied is a comparison between truth value and desire value. That is, what you want, match what is the current case, so you're satisfied. If they're not, you are not satisfied on that matter. And this no measurement is about what you believe before and what you see right now. Okay, and so on. So those things can be combined. Also, the major change will trigger internal feeling, so they will enter the system's internal experience. Then another group of mental operations is the system can create new tasks. From the very beginning, as described in many previous publications, that is, as a reasoning system, NARS processes 3 types of tasks. What we call judgment is kind of like new knowledge. It's descriptive knowledge or procedural knowledge with a truth value. Goal, we already mentioned, is what the system wants to achieve. And also question and query is about the system's truth value and desired value for a given statement. Okay, and those kind of things initially come from the input from the user interface or from the direct observation of a robot. And also the inference rule will derive new ones from the given one. So like every reasoning system will do that. Okay, but in this layer, we introduce a new type, which is not the traditional derivation, because in derivation, you always derive a new task of the same type. Is kind of your parent task. Say from judgment, you have a derived judgment. From goal, you have a derived goal. From question, you can have a derived question, okay, which is traditionally called sub-goal, sub-question, and so forth. Okay. But at this layer, we have the ability for the system to produce a new task of a different type from its parent, okay, which will be used to explain a lot of cognitive phenomena, which I list some of them here, which clearly we don't have the time to discuss them. Okay. And also, it can change the system's resource allocation. Those of you who know how NARS works in the previous implementation, you know that it's typically the control mechanism is based on dynamic resource allocation. That is, when you give the system a new task it never know before, it does not have a solution or algorithm. Instead, it uses a priority distribution among its concepts and beliefs to decide which one will be taken into consideration first, try to solve the problem. So it's not exhaustive search. On the other hand, it does not depend on existing algorithm for a given solution, a given problem. Okay, but that is not enough for complicated problem. For complicated problem, in level 9, we will allow the system to control its own thinking process. For example, what really get its attention at the moment will not necessarily be the one it will really think about next. Because for example, if the system noticed some novel phenomena in outside, which is, maybe curious. But on the other hand, it keep telling itself, okay, I have a task which I have to finish in 5 minutes, even though that task is kind of like boring, but I have to do it. So it can force itself to change its resource allocation instead of always go into something novel or interesting, something like that. So again, it can be used to explain a lot of phenomena. So this is what we call local operation because it works on an individual component, either a task or a belief and so on. Another group of mental operations is considered as global, that is for the whole system. For example, we also have global feeling, which is kind of like summarize the local feelings. So it's going to talk about the overall situation. So whether the system is overall satisfied about the level of is achieving its goals, and whether it's healthy in the sense that its body can be controlled as expected, whether the new situation is completely novel or in general novel or not compared with its previous expectation. Whether the system is busy with a lot of high priority tasks or not. Okay, so those kind of like overall evaluation will kind of give the system itself some indicators about its status, which eventually will be combined into something. You can call it happy or pleasure or whatever. It's kind of like an overall indicator about how well it is in its adaptation process. Okay. So this kind of thing is considered as an emotional state in the sense that it provides appraisal for the system's current situation, and also those appraisal will be used in the near future to guide the system's choice among different actions about different strategies. Of course, it's not the same as human emotion in terms of the content, but we claim that it serves roughly the same cognitive functionality as a human emotion. So they will serve as a condition and consequence. For example, when you are happy or not, your behavior will be systematically different at a system level. And also we can think those things as meta goals, but they are very different from the goals we talk about, which are concrete about what you want, what you don't, because they're implicit, they're not directly related to some specific thing. They're summary, and also they're at a meta level. Their goals are about goals in a sense, and also they are indirectly achieved usually, not directly. You cannot usually simply make yourself happy. Instead, you need to achieve a whole bunch of goals, then you'll become happy. Roughly speaking, like that. And also, they will influence the top level resource allocation policy. For example, sometimes the system will spend more time in its thinking about long-term goals, and sometimes it will spend more time on observation of the immediate environment. Okay, you need both, but NARS assume insufficient resource. Okay, so there is a competition between the two. Then how to keep a balance is not a fixed policy. Instead, it depends on the current situation. For example, when the system notices it is in a novel environment, in the sense that most of the observations are not what it anticipated, then it will spend more time in observation, meaning that to think more about what is seeing and what it means, meaning that how is related to other things within itself, instead of spending a lot of time about its long-term thinking process. So the system has limited self-awareness. This is consistent with the insufficient knowledge and resource assumption. This time, we're just focus more about the internal knowledge about the system itself. So now we can say that the system's knowledge about itself can be categorized, roughly speaking, into different status. For example, some of the things, the event that happened within the system, but the system is unconscious about them. This is especially like things described at the programming language level or the source code level. Okay. For example, the system is doing truth value calculation all the time, but is not aware about that because they're built in into the system, and those calculation does not enter into the system's internal experience, even though it's happening within the system. So they will influence the process of the experience. But if you ask the system why you calculated the truth value in this way, the system has no idea, unless you have future education, especially on that. Then you also have systems on subconscious and conscious process, and both of them are things that described in NARS and enter or may enter into the system's internal experience. But the difference is, again, there is a resource allocation. Okay, some of the things have a high priority, so we can say it's kind of like the system is conscious. It knows to a degree that what is thinking about. You can ask for it. Okay, and what you are seeing, why you make that decision, what you just did before a few minutes ago. And it can report that. And also, it can take that into consideration in its future plan. Say that, well, I have just tried that approach, which doesn't work on this problem, so I better do something else. But on the other hand, there are also subconscious things that since it's in the system's internal experience, but the priority is low. So it's only very, very briefly processed. So the system may not notice that, even though it was there, it has been processed. And the difference between this subconscious and conscious status, of course, is a matter of degree. On the other hand, the unconscious thing is kind of like there is a binary line between this and the other two. Okay, so that's the distinction. And also on the control side, also it's partial. So we have already mentioned the system have mental operations, which can have feelings, which is also some of them correspond to the mental goals. For example, the system want to be happy. Okay, I will try to do everything to make that happen. And also it can create some task by itself rather than just follow the built-in inference rules. By itself means that it goes through a decision-making process. And also it can, to a certain degree, attend to certain concepts and modules in terms of its resource allocation. So this kind of thing will be used as a supplement to the dynamic resource allocation, which I have mentioned before. That is, if you have no idea what you do, you basically follow what your attention bring you into, which will be influenced by factors like the strength of the stimulus and your motivation and the quality of your memory and so on. Okay, but with mental operation, you can do a certain degree of self-control. You can decide what you want to do. Okay, not just follow what your built-in mechanism lead you to. And another thing which we don't have the time to talk about is a skill acquisition. Okay, for familiar task, if this kind of thing can always be solved or achieved by, say, A followed by B, then followed by C, where A, B, C are all your operations, then you can take A, B, C as a sequence, as one unit. So you don't have to think things about step by step. You just call that subroutine. Okay, so that corresponds to skill acquisition, which is also already in the logic, but we haven't fully implemented or used it. So all of those together will give the NARS what is called a dual process in psychology. Okay, so there is an automatic process or unconscious process. You don't have to always think about what I need to think about the next, what I need to think about next. Okay, you cannot really survive in that way. So there is automatic process. But on the other hand, there is also a controlled or a conscious process, which will allow you to a certain degree, influence or change the automatic process. You tell yourself, I need to think about this, I need to think it in this way. Okay, so that will be a more powerful mechanism for control. So in the previous NARS, we already kind of like have the first one, but now with this level 9, we are going to add the second one. And clearly the coordination between the two will be a big topic, which will also be addressed by our future research. Okay, so that's the basic idea. We already have some publication, there's 2 articles, and also I had a book, and many of you know, Non-Axiomatic Logic, which was published in 2013. And a second edition now is in press, so it should be available within a few months. So in that one, a major change is the more recent development, including what I said today, okay, with more details. Okay, thank you very much. That's it.
Okay, so thank you for Dr. Wang's presentation. And any questions here? Yeah. Can you come here?
Hello, can you hear me?
Yes.
Okay. This is Olivier Georgeon from Lyon Catholic University. So thank you for, I don't know if you can see me, but
I
thank
cannot.
you.
Yeah.
Okay. Thank you for this nice presentation. My question is a very general question. So you have introduced this level of internal processing in NARS. And I know that NARS is about semantic emergence based on experience. I am interested in this topic. In fact, I often cite your paper as a reference for studying semantic emergence based on experience. And I have recently read Charles Sanders Peirce about semiotics, and he has those famous categories of firstness, secondness, and thirdness. And I was thinking, according to him, so the level of feeling would be firstness. It's just immediate sensation. And the level of experience would be secondness, because it's involved some form of interaction and a relationship between the agent and the world and events. And thinking and internal processing involves thirdness, because it's the construction of symbols and how symbols can represent an experience. So you need a third part. And I was just curious to know if you had thought about these distinctions from Charles Sanders Peirce, and if you have any opinion about these views.
Yes, that's an excellent question. But unfortunately, today's focus is on control, it's not on semantics, but I did thought about that. In a sense, I agree with Peirce's idea, but that's from a different point of view. That's more from a developmental point of view. That is, what comes first, what comes second, what comes third, and so on. So for individual system, if you think about it that way, clearly everything starts from sensory motor experience. There's no way to deny that. Then you begin to form some kind of abstraction higher and higher level. So you reach usually considered to be the symbolic level, which you use language and so on. But NARS is not developed to follow exactly the path of how individual get its experience. Instead, it's more from a logical point of view. That is, what is the simplest non-axiomatic reasoning system I can build? Okay. So from that point of view, actually, I start with a formal language. So Narcisse to start with. It just the sentence is very simple, just a term related to each other by copulars. And then I gradually make the term more and more and more complicated as I introduced today, which eventually reach the level of sensory motor. And some of the term can be the result reported by a sensor, and some of the term may correspond to an operator which directly work on the world. So in that way, the logic will be, to me, it's more easier to be introduced level by level and gradually become complicated. Even though from another point of view, actually several people have pointed that to me. So if you want to really duplicate what happens in the evolution process of intelligence in the natural world, you actually should start with sensory motor in the first place. And also for an individual person, also we start in that way. Okay. So what I mean is, in a sense, I agree with these 3 steps or 3 levels. And that also related to Piaget's idea about stage of development in children, right? I agree. it just, on the other hand, the way I design NARS, I'm not following the same order for some other reason. But eventually, in the system, you will see this two approach will actually end up the same. So the individual experience may come from, or a lot of them come from sensory motor. But I have to add another point, that is, I don't believe this reductionist approach say that everything have to be reduced into sensory motor to make sense. That's not the case. Many of things we get, especially the abstract knowledge we get from our linguistic channel, is not completely reducible to sensory motor, and they can still make sense. And that sense is kind of like grounded in our social experience. That's how people use those words to represent concepts, even though we don't have a mental image about what that kind of thing refers to. Not always. Right? So I don't know whether I have made that clear.
Okay, thank you very much for this answer. Yeah, the link between sensory motor, does all knowledge come from sensory motor or not? It's an open question. Yeah. Okay, thank you very much.
You're welcome.
Okay. Any other questions?
Hello.
Patrick?
Oh, yes, it's me. Long time no see.
Yeah. I cannot see you clearly, but I can clearly recognize your voice.
I have one question. A while ago, you also had this idea of operationalizing the control mechanism completely,
Yes.
like the way that each selection that is made in the inference process, be it task links, be it term links, that all of this would be encoded as individual operations, which could later be remembered or repeated.
Yes.
Do you still think that this idea?
Well, that's actually what I mean here. When I talk about limited self-control, let me share this again, if I can. Can you see the slide?
Yes. No.
Yeah. Actually, this is what I mean. But to answer your question with detail, you will need to read the new book. I really actually list which operation in the working cycle will be operationalized or which will not. You cannot really try to control every small step macro management over your thinking process. So what I have decided recently, actually, we haven't discussed that before, I believe, is to take several major steps, at least in this stage. I will try only to, for example, the selection of premise in each inference step. I will operationalize them. But instead of directly say, okay, I want to think about this, I want to think about that, I will just use some kind of it's a priming effect. I will increase the priority. So it's kind of like, now I need to think about this task. The system can do that. But the system will not go into the details, say, I want to think about this task and in its relation with that belief. That's a little bit too much. But I can prompt both of them separately, say, oh, okay, this is a new knowledge. I need to think about what it means to me. And also this task is important or urgent. I need to spend more time on that. With the hope that this tool will have a higher chance to meet each other.
This makes sense.
Yeah, again, I can send you the relevant part of the book draft, which I will actually tell you that which operation I'm thinking about. Clearly, they're not all, but I think as a first stage, at least in the next version, I will operationalize those steps so that those system will have some form of self-control without too much.
That sounds promising, and I'm looking forward to reading
Yeah.
it.
Yeah, I will do that very soon.
Thank you. Yeah.
And we had another question from a YouTube channel by the Artificial Intelligence channel, and they are asking, I suppose when events are conscious, you can ask questions about them, and you cannot ask questions about unconscious events.
That's right. I think I have already mentioned that. It's just you cannot ask the system why you use that truth value function instead of Bayesian theorem. The system have no idea. It just do it because it's built into it.
Thank you.
Okay, so there are two additional general questions. Maybe I can mention them here and we can discuss them after all the presentations. So one asks, hasn't NARS admitted defeat yet to LLMs? The second question, would there be any relation between NARS and LLM? That means, can NARS be explained or modeled by LLM, or on the contrary, can LLM be explained or modeled by NARS? Those two issues are mentioned by some friends online, so we can discuss those issues on the last general discussion session. So yeah. Okay, so let's move on. And so next we welcome Christian Ham, a PhD candidate at Temple University, whose research focuses on optimizing NARS through evolutionary algorithms. And in this talk, Christian will show how automatic optimization can free NARS designers from manually tuning parameters, allowing the system to evolve high-performing configurations for different domains, with applications including robotics control. So please give a warm welcome to Christian Ham. Okay. Christian?
Thank you, Bowen, for the introduction. Hello, NARS Workshop. Today I'm going to discuss the automatic optimization of meta-level and object-level NARS using evolutionary algorithms. As just discussed by Dr. Wong, NAL has 9 layers to the logic, but every NARS system or implementation of the logic into a real NARS system has 2 separate levels. The first is the object level, and this refers to the content inside of the system's memory, including its concepts, its beliefs, its goals, and its questions. And the object level is acquired during the system's lifetime by the system's experience. And then the second level is the meta level, and this is the mechanism that carries out the working process of NARS on the object level knowledge. So this includes the control mechanism of NARS, its architecture, its personality parameters, and other factors. And the meta level is differentiated by the object level by being built into the system from the start, and it can't usually be changed much while the system is running, compared to the object level, which does change as the system acquires new experience. And so we're going to differentiate 2 different types of adaptation, which are related but distinct from each other, which are learning and evolution. So the role of learning, or often what we refer to as intelligence, is to optimize the object level knowledge in a singular system during its lifetime. So during its life, the system learns by optimizing its knowledge base to better achieve its goals. And that's one form of adaptation. And another form of adaptation is evolution. And the role of evolution is to optimize an entire population of systems, such as in the meta level, but also potentially in the object level. And not within a system's lifetime, but rather over multiple generations, meaning that some systems will die and some new systems will be born with different capabilities. And evolution evolves to optimize these built-in capabilities or meta-level capabilities. So you use evolution to optimize or adapt your meta level, and you use learning or intelligence to optimize your object level. Although you can actually use evolution to optimize the object level too, in some respects, in the form of instincts or reflexes. So you can evolve like neural synapses, specific neural synapses, or in the case of NARS, specific NARS beliefs. And so in this presentation, we're going to we're going to talk about how we can possibly use evolutionary algorithms with NARS in one way, and then show the results of an experiment testing this method. So evolutionary algorithms, or EAs, are a very general method of optimization that can be used for any type of parameterized system. So you can evolve neural networks, you can evolve robotic bodies, you can evolve architecture and buildings, anything that can be parameterized, including reasoning systems. And so EAs adapt the structures or solutions that they're working on to maximize fitness according to some fitness function specified by the experimenter. So for example, if you wanted to evolve a very tall tower, say you had some sort of system that could evolve architecture or towers, and you wanted to evolve the tallest tower that's also stable, then you might have a fitness function and specify it to be higher depending on the height of the tower, and also potentially its stability because you want a stable building. And over the multiple generations, the towers or buildings should get taller and taller and more stable as their fitness increases. And so similarly, we can evolve a reasoning system like NARS by encoding its parameters into a data structure and then defining the mutation operators on that data structure. And this can be done in multiple ways. We're going to explore only one way today. But the style in which you encode these things, the way in which you define your mutation operators, the types of mutation operators, the value for your mutation rates, the design of your fitness function, all of these things all impact the process and the outcome of evolution. So it's not very technical. It's a little bit guided by feeling. So it's sort of a strange field. So we're going to talk about specific NARS genetic encoding. We're going to see a simple example of a genetic encoding developed specifically for NARS. And this encoding in particular involves both the meta level and the object level knowledge of NARS. And it's, like I said, it's only one example. There's lots of different other possibilities that could be tested and developed. And so in this specific encoding, a genome for NARS includes three substructures. Beta, which is the set of initial beliefs or instinctual knowledge, I should say. Gamma is the set of initial goals in the system, so it's instinctual goals or its seed goals. And then pi is a fixed size array of floats defining the values for the NARS personality parameters. So like evidential horizon K, the decision threshold T, these are all encoded in an array of floats. And we know that NARS operates using sensory motor contingencies of the following form. S followed by operation M leads to P, where S and P are sensations or events that are experienced by the system, and M is a motor action that can be directly realized by NARS. And the purpose of these contingencies are to represent causal predictions that by performing certain motor actions in certain contexts, NARS can use that to navigate the world or to move about in the world, navigate in the world. Basically, what this sentence is saying is if I execute M while experiencing S, then I will experience P. And usually NARS learns these contingencies at runtime using temporal induction. And this is highly desirable since this is the process of learning. But sometimes the learning process can be time-consuming, arduous, and even dangerous in certain environments. And so if we want, we can attempt to circumvent the learning process and give NARS background knowledge directly by ourselves, like in certain domains. This is fine, except the problem is that it requires manual labor from us. So we can automate the implantation of the background knowledge or instincts into NARS by genetically encoding object-level statements. And to allow evolution to build statements like this, it needs to know the set of primitive sensations S and primitive motor actions M, which are specified by NARS body, or by its sensors and its motors. So this is an example of a generic NARS genome containing sensory motor contingencies in the beliefs and a couple of goals, and also the personality parameters. So in this case, we could look at, say, goal 2, which is for NARS to desire event S7. And using only the content in this genome, NARS can begin already performing goal derivations on its instinctual genome content. So with goal 2, it might process with judgment 4 and derive a new goal, a new compound goal, GD, which is to say that when NARS sees event S1, it will derive to execute M3. So already just from looking at this example generic genome, we can see how the content of the genome can lead NARS to begin executing actions, certain actions, based on what it's observing. And this is a more concrete example of the encoding used just for a theoretical analysis, just to think about if we wanted NARS to do certain things, could we encode the statements in the genome and then get NARS to do that? And so this is like an ideal genome hand designed by a human, which would be me, enabling survival and reproduction. So this genome, we're not going to go over the specific details because it's sort of verbose, but it's basically saying these following bullet points. It's saying you have 2 goals, which are to eat and to reproduce. You should execute move when you see food or another NARS system in your visual field. You should execute eat when you see food very close to you. You should execute mate when you see another NARS next to you. And you should execute turn when you don't see anything. So you can turn around and look around the world. And theoretically, this minimum genome should allow a population of NARS systems to persist indefinitely and autonomously because they'll keep upkeeping their energy stores and reproducing. And we can think of energy as like the electricity in a robot. And so to go up to like a food item or something might be like plugging into an electrical outlet, analogous to plugging into an electrical outlet in real life. So that's what the survival aspect is. And then the reproduction is to perpetuate new generations of NARS and keep the evolutionary process moving. So as we just saw, hand designing a background knowledge in a genome like this, even for somewhat simple scenarios, is hard work. Plus, if we want to bootstrap more complicated behaviors, the genome might become intractable for a human to design, or the background knowledge. So then we ask ourselves a question. Can we instead automatically create these genomes using evolutionary algorithms? For this simple genome example, but also in the future for more complicated genomes. And so this question was experimentally tested using the genetic encoding we just saw by evolving both the object level and the meta level to evolve instincts and personality. In order to evolve the genetic encoding, we have to define the genetic operators on the data structure. And again, these can be anything. This is just some examples that I chose for the experiment. So for mutation, the system could add a belief to the genome. It could add a goal to the genome. It could delete beliefs and goals from the genome. It could modify beliefs and goals in the genome by selecting random terms from the sensory motor sets, and selecting a random term in the statement and then replacing it. And it could also modify the truth values and desire values of the statements in the genome by perturbing them by a small value or replacing them entirely with a small chance. Similarly for the personality parameters, which are also floats. That's for mutation, which is usually done after asexual reproduction. Then we have to define crossover for sexual reproduction. So for crossover, you take the two genomes as vectors, or the substructures in each genome as vectors, and align them. And then for each element in the genome, you roll a 50-50 chance to select the gene from parent A or B. And if one genome is too long, then you have a 50-50 chance to either select from the longer genome or from the no to include no gene from the shorter genome. So for the experiment, NARS was embodied in a simple wheeled robot. It was scored using a fitness function that encouraged food eating and reproduction. And then high scoring agents were kept by the evolutionary algorithm in case they were needed for the future. And also, in case we wanted them. If the population of agents dropped below 50, because all the agents were contained in a shared environment, then a new agent was spawned by the evolutionary algorithm. However, keep in mind that the NARS systems themselves were also able to contribute to the population. So it wasn't always an explicit evolutionary algorithm generating new agents. Also, NARS systems themselves could generate new agents if they were highly effective. Every NARS agent started with a small preset amount of energy that was continuously drained while the system was running. And NARS was able to replenish that energy or electricity by eating food or green food blocks, approaching them and executing the eat motor operation. It could also reproduce by spending energy, which was then received by the child so that it could go on and live. So the sensory motor sets were defined for the wheeled robot as follows. We have the sensor set S, which has 3 visual sensations for food, sensing food is near, food is far, food is not seen. Same thing with another NARS system, or in this case, it's called an animat since it's a simulated animal. The sensor could say an animal is near, an animal is far, or the animal is not seen. And then finally, we have 2 internal sensors, one stating that the energy capacity of the system is full, or at least filled to a high degree. And the second is that the system successfully reproduced. The motor set contained 5 operations, 5 primitive operations. Move, which causes a system to drive forward. Turn, which causes a system to turn clockwise. Eat, which causes a system to eat food if it was in front of food and nearby. Clone, which triggered asexual reproduction if the agent had high enough energy level. And mate, which triggered sexual reproduction if the agent had high enough energy level and it was next to another NARS system that was also expressing the mate operation. So we're going to first look at a qualitative example or a video of the NARS agents and see how their behavior changed over the course of evolution. So these are the initial NARS agents. And you're going to see that they don't move much. They're uncoordinated in their motor action, and they really just spam random actions or a single action. So you see here, they're not moving. This agent is flashing red, indicating that it's trying to execute a fighting operation, which I didn't mention, but that also exists. Here, this agent's flashing green, indicating it's trying to execute an eat operation, even though there's no food in front of it. And some of them are just spinning around. And blue indicates it's trying to execute a mate operation. In this case, in the correct context, because it's actually facing another NARS agent. So these are the initial agents. And here are the evolved agents. So now when you watch this video, you're going to notice that the evolved agents lock onto food visually, move towards it quickly, consume it quickly, and then reproduce. In this case, usually asexually, although there were a few instances of sexual reproduction, which we'll discuss in the results. Especially pay attention to this agent here in the middle of the screen. He eats some food, then moves on to another food, and then asexually reproduces. So now let's go over the quantitative results. 3 trials were run for 480 data points, which was about 2 hours for each trial. And then the results were averaged. So here we can look at a birth rate metric, or rather a percent of the population that was born by NARS. Remember that there were a population of 50 agents at any given time. So like this value 10% indicates that 5 agents in the population were born autonomously by NARS and not generated by the evolutionary algorithm. And you can see that over the course of the simulation, the ability for NARS to reproduce itself, to survive and reproduce itself, increased. And by time step 300, about 20% to 30% of the population was being maintained by NARS autonomously. And here's some more relevant stats related to survival and reproduction. So starting at eating no food blocks at all, the average agent eating no food blocks, by the end of the simulation, the best agent was eating up to 3.5 food blocks during its life, and the median agent was eating 2.5 food blocks. Oh, sorry. I can't see the title. But it's actually the same. It's actually the same here. So the best agent was eating 3.5 food blocks during its life, and the median agent was, eating 2.5 food blocks. It looks like the values are very similar in the asexual reproduction graph as well. The average agent was reproducing about 3 times asexually, and the median agent was reproducing about two times asexually, which makes sense because the amount of food eaten is proportional to the amount of times that they are able to reproduce, because some of the energy has to be gifted to the offspring. And there were actually surprisingly a few instances of sexual reproduction, which is kind of interesting to note because it's a little bit more difficult and more rare. Again, both agents have to be expressing the same action. They have to be in close proximity. There is a benefit to sexual over asexual reproduction, which is, first of all, the recombination of genes. And secondly, that each parent only has to use half the energy cost, since they'll combine their energies to give to the offspring. So there are some benefits to sexual over asexual reproduction, although asexual reproduction usually is preferred because it's a lot simpler. It can be performed at any time, and it actually produces a clone of the parent with a slight mutation. Whereas recombination can make some some genes which are not stable, some genomes which are not stable. And so here are the meta-level NARS parameters and how they change over the course of the simulation. So for the K value, or the evidential horizon, we can see that it didn't really change much. This is max, not meaning the best agent, but rather the maximum K value stored so far by the best agents. So we can see that the median K value stayed around 1, and that's where it started as well. So the K value didn't change much. On the other hand, the NARS T value, or its cautiousness value, or its desire threshold, different names for it, this value did change, and it decreased drastically over the course of simulation from starting around 0.5 going to down to about 0.45. And this is interesting because the outcome of something like of the T value decreasing makes NARS more prone to action, because the goals don't have to have as high of desire values to be pursued. And so likely what was happening was at the beginning of the simulation, the agents were too inhibited or didn't have high enough desire values to really do much. And so the evolutionary algorithm adapted or coped by causing the system's desire values to go down, allowing them to be more prone to action. We can also look at the number of beliefs that were initially given to each agent, or the size of the background knowledge effectively. This started around 5, like a random, they were all given random distributions. It seems like the median was around 5 beliefs per genome. But by the end of it, they evolved a more and more number of beliefs up to about 8. And this makes sense because obviously it provides NARS with more knowledge to bootstrap it and get it to start surviving and reproducing faster than just by learning alone. So in conclusion, a genetic encoding was developed and tested for NARS. The encoding was then tested in a simulation experiment for 3 trials, and the results were positive. Evolution resulted in a population of simple NARS robots capable of survival and reproduction. The results indicate that NARS evolution is possible and effective. In the future, directions should explore more complicated situations. And thank you.
Okay, thanks, Christian. Any questions on Christian's presentation? Yeah, sure.
Should I go there?
Yeah.
So hello, can you hear me?
Yes, sir.
So my name is Kirill, Constructor University, Bremen, Germany. So my question is about the amount of food in your experiments. So my understanding that the amount of food will be essential for survival. So if you have limited food, the survival algorithm would be 1. If you have different amount of food, it would be a different strategy. So is your experiments play with this food availability somehow, or it's kind of topic for the future investigation?
That's a good question. I do think that's a topic for future investigation. Mostly I provided them with a plethora of food, as you can see in this video, sort of surrounding them. So that survival and reproduction was very, very possible for them to achieve. I still spawned them a certain distance away from the food to ensure that an agent couldn't just spawn there and get a high fitness score. So they were spawned a certain distance away, but there was still a large amount of energy or food available for them. And I think it's a important topic because if this is what their goal is, by making food or energy harder to acquire, the agents should then be able to, or should be forced to acquire greater capabilities in order to reach that food. And that is something I do want to play around with in the future. Thank you.
Yes, so because my understanding that the experiment should show the adaptivity of population to different amount of resources, right? So thank you.
I agree. Thank you.
Okay, so thank you, Christian, for demonstrating how evolutionary algorithms can accelerate NARS development. So our third speaker is Tanrui Li, also a PhD candidate at Temple University. And Tanrui will address a timely and important challenge integrating NARS with large language models. While large language models produce impressive outputs, their reasoning processes can be, flawed. And Tanrui will introduce two novel approaches, one based on the neural symbolic backbone using non-axiomatic logic, and another focused on learning human interpretable control through exploration, both aiming to make large language models outputs logically grounded and interpretable. So please welcome Tanrui Li.
Hello guys, can you hear me? Hello, can you hear me?
Yes, yes.
Got it. Thank you so much. Hello, AJ25. And today our topic will be about combining NARS with logical models. And as we all know, adding logic part to logical models is not fresh. It's an old topic. But today we're going to have something different. I'm going to add a hot sauce of NARS a little bit to that. And let me introduce myself again. My name is Tanrui Li, and today I'm your chef. Okay, today we're going to have a two-course dish. Let me start. Oh, can you still see the screen? So there are some animations. I hope it will work. Let me check a bit. All right. And okay. Let's keep it this way anyway. Okay, today we're going to have a two-course stage. The first will be, actually there are two methods. The first will be introducing NARS in mixture of experts for consistent semantics of experts. And this is a neural network friendly, since the backbone is still neural network. And if you're working on neural network specifically, introducing this method will not harm your backbone. The second method is about learning from the behaviors of logical models in NARS. It's just much like we're going to teach NARS with logical models. But in this teaching, it's not by parameters. This is by observation from the behaviors of them. Therefore, if it's possible for NARS to learn perfectly, then we will have something with exactly comparable performance, but totally interpretable and controllable. Here we go. First, I want to talk about something about the mixture of experts. Okay, the mixture of experts is just a method, and it's a part of this method is discovered to let you save the updating of some parameters. Things like example over here, we have a router, and the router go to expert one, and expert one is selected for the following calculations. Therefore, in updating, expert 2, 3, 4 are out of business. Therefore, you just need to update a part of the parameters and choose a catastrophic forgetting. But another part is that people don't like to say, hey, this is the expert. The expert must have some expertise. Therefore, this neural network is explainable. So whatever, like in this way, at least more explainable than before. But the problem is that there is an expert with some expertise, but for example, this is a calculation that in the pipeline, right? For example, this expert is perfect at calculation, the AND operator, some OR operator, or something like this. But what expertise? We don't know, since they are just parameters. On the behavior, we may say 99% of it acts like the perfect AND operator calculator, but on the remaining 1%, it might be work for OR operator or something else. We cannot explain that. So we need to add at least some stable expertise to make sure, hey, you're an expert, you're good at something, and we want to keep it for this expert. To do this, before we need to have some probe. It's called the linear probe. Say here we have 4 experts, expert 1, 2, 3, 4, and we have some very linear probe activation network to say non-trainable subnetworks for this one to give the calculation, but in the end, I want to calculate some scalar values. So example, for expert 1, the probe activation is 0.8, expert 2, 0.7, expert 0.2, expert 0.9. So actually means that here we have 4 different expertise categories for each expert. And in the calculation, the expert will vote whether this is suitable for my expertise, like shown in this bar chart. And based on such activation, we can discover some interesting ontological structure between experts. For example, if we assume that expert 1 is always activated when expert 2 is activated, but not on the opposite direction, what does it mean? Let me make an example. Expert 1 is for, fruit. Expert 2 is for apple. So when something is apple, it must be something at the fruit, but not in the opposite direction. For such a thing, we may discover some ontological representations represented in narcissus exactly. Say E1 is a kind of E2, but not on the opposite direction, something like this. And such a thing we can use it for reasoning and to derive something interesting. Say, okay, for example, in a layer of some experts, it is possible for us to discover some relationships like this. For the details, I'll keep for the second method. We'll talk there. Okay, we may discover some ontological relationships. This is the most straightforward thing. We have more profound one, but maybe not very good for visualization, whatever. For such a thing, and okay, and for such a thing, we may say, sorry about that. And for such structure, and we know that some experts just the special conditions or more general conditions of some others. Therefore, when we just put the data into the neural network to calculate the first activation, the first probing, and it is possible for us to give that one to the structure and following the calculation. Say, if at the beginning, this one would like to say, oh, now the input is an apple, and it's also a fruit, and which is consistent with the overall structure of such a thing. And then we vote yes for that to say, yes, good, true. This is a consistent answer. But how about there are some input that which is voted yes by an apple, but voted no by a fruit? This is problematic. So what are we going to do? Is the next question. Here we have two. Options. The first will be, we'll say, okay, yes. From our previous example, we understand, yeah, fruit, apple must be fruits, true. But the problem is that over here, these experts, although we can see they have expertise, since they are bounded by this, they are involved in this structure, and but the problem is that this expertise are not usually interpretable. They are not grounded in human language. We know they have some stable expertise, but we don't know what they are. So we cannot just say, hey, this is consistent with human understanding, and let's just keep it. No, impossible. The problem is that we may discover some relationships. They are stable. If they are stable, let's just enforce it to say, if we find some relatively correct relation, tested on so many training data, in new data, if it is not followed, we may enforce the new data to say, if something is an apple but not a fruit, let's just using the loss function to make this one is also an apple. Is also a fruit, like this. But on the other hand, if some relations are not stable enough, it is better for us to consider let's just changing the expertise of some experts and refreshing the statements. And such structure tested primarily tested on this very simple data set. Here we have 10 CNN experts, and we would like to discover some relationships between experts to say, yeah, in recognizing handwritten numbers, and we may have some experts And now we have the ontology of such experts. And for each input data, we may enforce such a thing. But this is an intermediate result. And for further result to say, to observe which CNN is working on which part, since that's why I chose to work on this very simple example, since we can see that the part that is focused a lot on each CNN network to say whether the experts is really an expert. For example, this neural network is super good at recognizing circles, something like straight lines or whatever. But I mean, I think if so, it will be so real cool. But currently, it looks like, but I'm not sure. I think they are not grounded with human language. Probably neural network is working on some very strange patterns that we cannot understand. Okay, this will be the first passer. This will be the first semester. Say you're going to keep the neural network. Since you just need to add some linear probe activation networks to discover, and NARS to discover the mutual relationships, maybe not mutual relationships, and use NARS reasoning engine to do the calculation at each round of forwarding to give additional consistency loss functions. And well, have the downstream task finished, you can also have a globally consistent structure of these experts to make sure they're really experts with a stable expertise. Okay, on the second hand, if you are not a fan of neural networks and you don't agree with the way that how neural networks generate the output from the input, it is okay for us to introduce the second method to say, well, let's just let NARS learning from the large language models to say, we observe the input, we observe the output, but here we don't put them in a black box. However, we put them in a white box to get a solution. How could this be finished? Before that, we need to introduce some preliminary background knowledge, like we mentioned in Dr. Wang's talk today about sensory motor channels. Here, we may have two sensory motor channels, say the observers of NARS. NARS would like to look at these logical models, and here are two channels. First, I'm sure just two examples, okay? The first channel might be for input of neural networks. The second channel might be for the output of neural network to say, NARS would like to say, hey, I give you this input, what kind of output I can achieve, like this. For example, for logical models, and we may give them in, we tap into the system in different paces. Say at the T1, at T0, we give the first sentence, and at the T2, we give the second sentence. It is not necessary that for each atomic observation being just a single word, it can also be a sentence. And at the end, we have finished inputting. And on the other hand, we can observe a response from the neural network. Then the problem will be, as expected, it would be nice if we can see, yeah, from this kind of sentences, for example, I just ask the robot to go to the right corner, and we can have the corresponding operation sequence as a response. True, but the problem is that, first of all, they are just instantiational answers. How about if I change the environment a little bit, but with exactly the same input? For these more complicated situations, we can add more channels, but we'll talk about later. Here, okay. Here we just focus on the second question to say, okay, now I get some input and I get some output. How could I build a potentially causal relationships between them to say, if this is the first sentence to lead to the response, or this is the second sentence to lead to the response. For example, the first sentence might be, hello, LLM, I have a question for you. And the second will be the content of the question. So in this case, we need to know which part of the input, including their combinations, will lead to which part of the output over here. Very combinatorial, exhaustive problem. But we can definitely not just enumerate everything, right? It isn't so prohibitive. So the problem will be, I'm going to introduce something called subjective results allocation, which is related to Dr. Wang's today's talk about the ninth level of non-axiomatic logic, to see your feelings over that. But here, I did not go too deep details, so let's just talk it in a general way to say, here, generally that means here I don't want to differentiate the terms, the terminology is about to use. Let's just see everything in the plain language. Okay, subjective results allocation. Before we talk about that, let me introduce a small story for you. Say, before Newton discovered the law of relativity, I think the apple still falls to the ground, right? That is because, but why nobody discovered it before? That is because before that, people will not consider the law of relativity in our daily life for more profound thinking. I mean, it is not necessary, I was thinking. That's the reason that why we start by just learning from the behavior of the logical models. And people may ask why you don't take, I mean, logical model is not just based on their input and output. They may have some intermediate, super interesting intermediate results. Why you don't focus on that? The problem is that at the beginning, it is not necessary. These things are also provided to the system like this. We may have something not very related to the problem, but it might be useful. But when they are necessary to the question, I mean, when they are worthy some results, worthy some calculation results, then we will focus on that. Otherwise, we will just leave it. So, and by this part, I would like to give the name called subjective results allocation. Say, for this, I mean, if we're going to read this sentence, and let's think about these are broken texts, and we may say, considering the first three words will be meaningful. Say they are just meaningful things. Looks good, and let's just put into looks good. And if it feels like it's a good thing, on the other word, to say if we find something that probably will make the system happy, then we can keep thinking more about it. Otherwise, if we don't think, if we don't think it will work, we will just skip it. Here, you might have another question. Say subjective results allocation. Why you want to do something subjective? Since subjective means usually the opposite of reasonable, but no, here the case is that the subjective part is just for the feeling of the system. Say, at the first glance, I will think it will work. Then I will attempt to put more results to such a thing for the system to dig deeper. If it really will work, then there are two things. First, the problem solved fluently. The second is that my feeling is correct. And so in the next part, without thinking, I can trust more on my feeling to give it more results to dig deeper to get a correct result. Now, on the other hand, if my feeling is not right, to say if this is very important, but I don't feel like it, so I did not give it enough computational results, or if it's super not important, but I give it more computational results, this will give some feedback to like the system. That's to say, to correct its feeling. So don't think about it this way. So the details of how the feelings are corrected, I think Dr. Wang gave a very clear description of that to say, yeah, we have internal buffers to have a right called operationalize of the system thinking, and then we just do something about that. Okay, and the process will usually be like this. We may have multiple goals and probably conflicting with each other, and based on the internal experience, what I have thought before, and the performance of the outside world, things. This is why important it is for NARS to connect it with the external world to do something concrete. Otherwise, how could NARS know whether I did a good job? I think Dr. Wang mentioned that there are some internal evaluation to that. So how about the satisfaction of the system, and how about the whether the system is busy enough, something like that. But there are also some other external requests about that, and based on those very complex and mutual related goals, and we may have an evaluation of how the system is thinking, and then we change the results allocated to channels and change the results allocated to maps to correct the system thinking, to focus on something that would make it progress, that would make it some progress. And here, I did not have very good demo examples like Christian, but here is a plan of that. We have a gray word, and we have instruction. Say the gray word is the first channel, and the instruction, the second channel, and the large momentum response, the third channel. And we may try to learn that from the gray word and instruction, and which large model response will be generated, and try to learn from that, and try to learn from such a process. And a good news is that For such a thing, for the instructions, this can be built gradually. So at the beginning, we just have some very simple instructions that NARS can learn easily, which is useful as new bricks for building the more profound comprehensions of the large language models behavior. That's all. If you're interested in more details, just let me know, and I'm glad to share. But just for today, and since 30 minutes and 2 topics, so I did not involve too many technical details. And do you have any questions? I'm glad to help.
Okay, now, so sorry, there's no question from this room, and also no questions from the YouTube live. So so we'll move to the next presentation. Okay.
Thank you so much.
Yeah, thank you for sharing those innovative strategies to combine symbolic reasoning with modern language models. And so for the next presentation, I will be stepping out of my role as the host and putting on my researcher hat. So my talk is about spatial sense and objects. Let me share the screen. Yes. Oh, okay. So, okay. Yeah, this is our work accepted by this year's conference, and it's titled "On the Essence of Spatial Sense and Objects in Intelligence." So it's generally speaking, it's about how an intelligent system can learn objects, physical objects, and as well as space. So you don't assume a 3D space in mind, and can you just learn the structure of a 3D space? So that's basically the question I want to address. Although we don't have a perfect, a perfect solution, and you will see there are some interesting results. Especially, we have some, we form some normative theory to use a logic to model the representation of objects and the representation of the space, and it provides some possibilities to for an agent to learn the spatial structure and the objects residing the objects in a space. Yeah, first of all, let's see what are the traditional views. So traditionally speaking, space is the medium or frame where objects resides. So it's very natural for us to assume a 3D space in AI research, right? Like robotic navigation or image recognition. You can assume a 2D or 3D space, and then based on that assumption, we can form some representations of objects. And traditionally, objects are things or entities in the outside world. It's something as it is, it's some objective things in the world. And yeah, so in the traditional AI studies, they often assume this implicitly For example, you know, in convolutional neural network, they usually assume, implicitly assume a 2D structure or picture, so that they can use convolutional, you know, convolutional computation, and then, you know, can do the following processing. And also, YOLO networks also use a neural network to learn to, you know, predict the position of some objects. Then the position of an object is two-dimensional. So in this work, they also assume a 2D space, or at least a 2D space of the picture, you know, in their framework. And another classical example is robotic navigation. For example, you know, automatic driving, or robotic, like you make a robot to go around, and there's often an assumed map in the mind, or it assumes a space in the mind, and the task is to feed the space, you know, just put the environment around into that space. So they often assume a 3D or 2D space in their theory. And in neuroscience, like I'm not sure if you know this famous work of Greek cells. So they found that some neurons in our brain may respond to some positions in our, you know, in a room. Like you can see the picture in the middle. So a rat move around you know, a platform, and if you just measure the activity of a neuron, you'll find that a neuron will just get excited when the rat goes when the rat reaches some places, and if you mark those places, you will find that they forms some pattern, like the blue points here. And so there are some models which aims for revealing the principles of this phenomenon, and they assume that there is a 2D space, and the task is to map the you know, the outside position into that internal space. So all of this works. They assume a fixed dimensional space in their theory. And another famous work is capsule network. So Hinton, Geoffrey Hinton, he found that neural networks cannot do well in spatial generalization. And for example, you just shuffle the positions of our face, the components of our face, but for a convolutional neural network, it cannot recognize the difference. So they developed a new architecture, neural network architecture named capsule networks. But their work, so in their works, it's hard to evaluate whether the model can, you know, whether the deep neural network can model the outside space very correctly, because it's a black box or gray box. So it's lacking of interpretability. Yeah, so that's why we want a normative theory that offers a unified account of space and objects. And so this is why it's so critical. And it can deepen our understanding of how the mind interprets the world, especially how we interpret the space, how we can, you know, we can understand and we can learn and understand there's a space around here, and also why it's 3D or why it's 4D or 2D. And also it may inspire the future development of AGI systems that can generalize knowledge to normal things through their understanding of space. So in the following, I will, follow this route. I will firstly introduce some philosophy about space, about objects and space, and then I will provide a formal theory based on an axiomatic logic. And finally, I will provide some illustrative examples to, explain the theory. Although these examples are not the implementation of a complete AEI systems, but I believe this might inspire the future research. So yeah. So the core idea here is both objects and space are constructs of subjects. What does that mean? So we don't need to assume some innate objects, and we don't need to assume innate space. Without this assumption, a system can still learn there is a space around, around it, and there are objects in the space. All of those things are acquired rather than designed or innate. And the essence of an object we propose is the positional relations among its parts. And each of the parts is also an object. So it forms a recursive structure. And at the lowest level, it might be a pixel or a neuron, which a sensory neuron. And it can after you convert the representation into a concept, then you can compound it and form some higher level concepts and which represent an object. So next, the essence of spatial sense or identically space is the sum of equivalence relations among changes in positional representations. So this is, I think this is kind of hard to understand. So let me explain it. So changes in positional representations, what does that mean? So the positional representations are modeled by our motor, say our body sense, like our how to say that, proprioceptive representation. So for example, when we raise up my hand, when I raise up my hand, then I'll feel something, right? When I put it down, I'll feel another thing. That then the difference can be represented. And so this is what I mean, the changes in positional representations. If you think when I raise my hand, my feeling of my body can be represented through through a vector or a concept, whatever you want, you use. And when I put down my hands, you can also have a representation. Then you can have the changes of the representation, right? So this positional representation exactly means the representation of your body position. And if you can represent the change of your body, then a space or spatial sense is the sum of the equivalence of those changes. For example, when I move one step from here to here, I have a body representations change, right? But if I move from here to here, I also have a representation change. Then we can form the equivalence from the previous change to the current change. Then those two changes are equivalent. And if the system knows they are equivalent, then this is a preliminary spatial sense, right? Just assume we are in a space and we found that no matter where we start, if we have the same body change, then we can feel the same we will have the same feeling. Then those feelings are the feelings of spatial sense. Okay. Yeah, so those are the core ideas of this paper. Both objects and space are subjective. They are the constructs of subjects. But why do we have that position? Why do we have that point of view? I think this is, I will firstly introduce the object section, its philosophy, why I think we should focus on the subjectivity of objects, and also how to formalize it. And then I will move to the next section about spatial sense. Those two sections are highly related because how do we know we are in a space? Because we see some objects there. There seems a medium of frame where the object resides, and how can an object reside there? Because there seems a medium so that the object can exist, right? So these two topics are highly related, but we should start from somewhere. So let's now see the topic of objects. And the first issue I want to discuss is about subjectivity and objectivity. So to build an AGI system, which is the better viewpoint? Should we think every object is objective, or should we think every object is the subjective construct of our mind? I think, yeah, I put a list of thought experiments here. They are from some philosophical materials, the first one is Russell's turkey. It's a famous thought experiment. It says there's a group of turkey and there's a scientist turkey, and it found that every morning a farmer will give them food so they can draw a conclusion or derive a natural law that every morning when they see the farmer, they will get food. Okay, this is for our humans, or from the perspective of God, this is very ridiculous. This natural law is ridiculous, but this is only what the turkey scientists can know. And someday the natural law is broken because the farmer just kill one turkey and eat them. Yeah, so this thought experiments reveal the limitation of our experience, and in other words, even if our natural law or scientific theory are the subjective summarization of our experience, although those summarization or description are more systematic than other experience or other descriptions. And the next thought experiment is called what is like to be a bat. You just imagine you have different sensory channels. You don't perceive the world using your eyes. You don't have your body, but you are now a bat, and you can only you can only sense the world using your ears, by sending some voices. So if you have a very different sensory channels, will you have the same understandings of the world? That's a question, and I think you will have very different understandings about the world. And this means, our understandings to the world, no matter its object or its space, are still subjective constructs of our mind. And another another thought experiment is about color. So if you are, the same color like red in different people's eyes may looks different. For example, if I say a green thing, I call it red, but you call a red thing green, then through communication, you can make a difference. You cannot know, or we call the same thing, but we have different feelings. And this thought experiment also reveals the subjectivity of our mind. The last thought experiment is called brain in a vat. So you just suppose you are now in a vat, or you are like a mat or a matrix. So you have some electronic signals into your mind, but you don't know you are in fact in a vat. You just have a brain. You don't have body, but all of them are illusion or hallucination. But you cannot make a difference. So this thought experiment teach us, whereas we are a machine, or a machine. We are a machine who is processing our experiences rather than perceive a real world. We cannot say the world is real or not. So based on this thought experiment, I think the subjectivity is more important for AGI systems. Yeah, so that's why I adopt a constructivism view. And so based on this view, the next question is, for an AGI system who is interacting with the environment, so what should be designed and what should be learned? Or we can say, what's the part of intelligence and what's a part of skills? So intelligence is something independent of our experience. We can, so for an AGI system, intelligence is what we design, what we, the code we write. It cannot be changed by the system itself. However, on the other hand, skills are acquired. It's modified by the system according to the experience it has. Now, for perceiving the world, especially to perceive objects and space, what should be innate and what should be acquired? I think that's the most important question for AGI research. So even though the world may evolve in its inherent way, that remains independent of a subject's beliefs and desires, and it may constrain the behaviors. But any description of the world is inevitably subjective, right? Because we have some unique sensory motor channels. We have unique sensors, unique effectors. We have insufficient knowledge. We don't have unlimited time. And we have our own motivations which guide our attention. So different subjects or different systems' description to the same thing may be different, right? Or every description is inevitably subjective, okay? And all descriptions are determined by those different factors, and making it makes it impossible to claim that any description is the sole correct standard. Nonetheless, some descriptions might be richer or more practical due to more extensive observation, and some descriptions expressed in natural language may become common sense, or some facts or scientific theory in a certain population. Okay, so in this view, an object is not something as it is, but it's a concept as the summary of subjective experience. But this concept is different from other types of concept because it directly stems from sensory motor experience. And an object concept is initially a summary of the positional relations among its parts. Like if we if we want to recognize a triangle, then we need to recognize different positions, positional parts. Like we have a vertex here, here, and here, right? They have different positions, although there are some sharing patterns. And the meaning of a concept may evolve through time, and this property also applies to an object concept. For example, this is a phone, mobile phone. It's an object, right? Usually we think it has a certain shape, but sometimes we can use it to to break something. Now it has some additional usage or utility. So that means even if for a object concept, we can still form some causal relations using this concept, okay, using this object concept. And those causal relations are formed later and are formed after they are formed in the lifetime of the system. And that's what I mean. It can be connected with other concepts forming causal relations, or you can call it affordance, etc. Okay, so now let's give you some formal description. So here I ground the theory to non-axiomatic logic, and so an object term denoted as P or simply object is a type of term that summarizes the relations among its parts, and each part is a property that contains an object. You can denote it as CI. CI is the i's part, and each part is attached with a spatial attribute PI. This PI is the positional attribute, or it's a representation. It's a internal representation, and that position is relative to other parts of positions. So there's no absolute position, or you don't have to assume a coordinate from the beginning. But you just need to have some relativity. You just need to have some relative positions. And if you are familiar with non-axiomatic logic, you can have its logical form like this. But intuitively speaking, you can see the picture on the I think it's on the left-hand side. So you see there are some white pixels and black pixels. You can view them as different types of concepts. A white pixel is a concept white, and black pixel is a concept black. And each white concept has a positional attribute, like it has a special position in the picture, but you don't need to have the coordinate like x, y. You don't need to have that. You just need to know the relative position with other parts. Like you can see there are three boxes, each corresponds to a feature attached with its relative position, and you can move your eye and go through every point, and then you just move your eyes, you just change your internal positional representation, and then you recognize, oh, there's a certain pattern like this. And then you can, compound those three parts into a whole one. And this whole one is a object, but simultaneously it can be a part of a higher level object. As you can see, the three parts of the red boxes can be compounded into a green box, or we can say it's an object. And you can see the picture on the right-hand side. There are also several different green boxes. With each of them corresponds to a part, and then all of them with different relative positions can form a new compound which corresponds to a concept. And we can name this concept 6. So yeah, so this process can be fully modeled by non-axiomatic logic, and the lack of each part is not deterministic. It's not. Even if you miss one of them, you can still recognize the whole thing, because the reasoning rule involved here is weak reasoning. Specifically, it's induction rule. So for induction rule, you just collect more and more evidence. For example, here you have 6 boxes, you have 6 pieces of evidence. Even if you lack one of them, then the whole thing is still there. Okay, you can still recognize as a 6. And also, if you have two objects, but they have very similar positions, relative positions, then you may view them as the same thing. This is what this definition means. And so with that definition 1, you can represent an object using this form. Then this theorem expresses how to recognize an object. For example, you have 3 parts A, B, C, and you have a concept P. A, B, C are components of concept P, which means P is a prototype in psychology. And you have an instance S. S is a concrete object, and you found that this instance also has 3 parts A, B, C. Then you can use the abduction rule and derive that instance S is similar to the prototype P. And this process is based on the induction rule. So it can be fully modeled by non-axiomatic logic. And another interesting theorem is that you can predict other parts with a certain observation. For example, a human face. When you see a human's eye, then you may predict there might be a human nose in a certain position, right? So yeah, I don't want to dive into details, but this theorem just says you can predict other parts with a certain local observation. So another implication, very interesting implication, is the difference between causal relation and part-whole relation. So in this formal theory, it's very obvious that causal relation is different from part-whole relation. So formally speaking, causal relation can be expressed as this, like C1 and C2, and arrow, and a right arrow, and then C3. This means if you observe that C1 and C2 occurs subsequently, then you can predict that C3 will occur. But if C1 doesn't occur, then the following chance will be break. You cannot predict anything if C2 doesn't occur. So this is what causal relations mean. If you lack some part, then you cannot derive the, the final conclusion. But the story is different in part-whole relation. For part-whole relation, even if you lack some observation, for example, you have a human face, but you don't see the one eye. For example, it's being masked, but you can still recognize the whole thing as a human face. So yeah, so every part of an object is not deterministic. It's not will not significantly influence the final recognition, but it just provides some evidence. Okay, here are some examples. Like we can use the theory to to recognize some handwritten digits. We just put the MNIST digits into the concept network, and using the theory and the reasoning rules, you'll see that there will be some prototypes learned by the system. For example, if you use supervised learning techniques, you can learn you can learn those prototypes on the left-hand side. Also, you may use unsupervised learning techniques. You can also learn some patterns. Okay, and another experiment is about eye movement. For example, if the system has learned a prototype, a triangle, and it's composed of 3 vertices, and the system, the task here is to recognize that triangle using eye movement. It just scan through the whole perceptual view and try to recognize something, but each glance it can only recognize a vertex or just a small part, and then it should collect the evidence of the whole of the whole path, and you'll find that most of the time it will converge to that triangle, but sometimes it may just get disturbed or distracted, and then it will move. Just try to see somewhere else, somewhere else, and see if there is a new observation, and it sees nothing, then it comes back to its familiar pattern. So these examples may provide some intuitions on this theory, or at least it can prove that this theory is useful. And next is about spatial sense. We in the previous theory, we assumed that each part is attached with a spatial attribute, right? But where does that spatial attribute comes from? So do we need to assume a fixed dimensional space and then maybe use a coordinate to represent, use a 3D space, and use vector to represent a point in a space? So this problem disturbed me for a long time, and a few months ago I found that there's a very genius solution in the cognitive science field. So and I got many inspirations from the work about sensory motor perception, and here I think we can also start from the philosophy. Should a space be assumed, or should it be acquired? If you read some philosophical papers, you will find a famous book, Critique of Pure Reason, by I think the author is Kant, and in his view, space is a priori, which means if you want the system to perceive the world, you have to have some assumption of space. You have to have a framework of space in your mind, and then you can learn objects. But is that really the case? Later I found that another school, it's called sensory motor account of perception. So in their perspective, space can also be learned. So how can it be learned? We put it we can discuss this later. But now we just consider which viewpoint is more suitable for AGI. And I think we can consider the goal of research. So for AGI research, there are two different goals, and every project, have to find a balance between the two goals. There are engineering goal and the scientific goal. So for the engineering goal, we want to build a machine, a thinking machine, which can, help humans do something like large language models, and we hope it to interact with the world. And for the scientific goal, we want to understand the mind itself. We want to understand how we think. Okay. So in this perspective, I think the latter viewpoint, sensory motor account, is more suitable for AGI, because if a human doesn't have to assume a space in its mind, then how can a human learn a space? This question may deepen our understanding about how we learn the space, or how we can understand a space. And in addition, if we have a machine which can learn the spatial structure, then this machine will not be limited to our 3D world. Maybe it can jump into a 4D or 11D world, or maybe a quantum world. I don't know. So it may be more adaptive and generalizable. Yeah. So if we want to drop out the assumption of fixed dimensional space, then is it possible for us? Is it possible for a AGI system to learn a spatial structure? So I think we can have a thought experiment here. You just assume you are your soul is injected to a machine. You can feel nothing. It's black. It's empty. You can feel nothing, and then some sensors are plugged in, so that you can feel some light or light spots. And you found that those light spots are changing all the time, and maybe we can call this exteroceptive representations, because it can feel the lights from the outside world. But later, some other light spots just comes into your mind. You find that you can control those light spots. Like you can raise your hand or put down your hands. You can control it, but when you control it, you will get different representations. We can call them proprioceptive representations. And let's denote a pair of exteroceptive signal R and a proprioceptive signal P as a pair RP. And through learning, you'll find there seems to be a pattern. Like you find that you have a RA and A, like you have a representation in this position, and RBB which means you have another representation RB with position B, you find those two pairs always occur, they always occur simultaneously, so that you can induce them into a pattern. And gradually you find that some patterns seems to be equivalent. For example, you have RAA, RBB, this pattern is equivalent to RAA prime and RBB prime. You see the latter one, they have the same representations, RA and RB, but different relative position, A prime and B prime. So you can abstract them into a new statement. AA prime is equivalent to BB prime. What does that mean? That means the internal movement from A to A prime is equivalent to the movement from B to B prime. So you don't know a Euclidean space. You don't know a 3D space, but you know that this move is equivalent to that move. Just as a ball move from your left-hand side to the middle is equivalent to the ball move from your middle to the right-hand side. Okay, so this statement AA prime equivalent to BB prime is what I say the equivalence among changes of representations, positional representations. And you can just extend this example into a more general case. You'll find plenty of movements or changes of positional representations, and you form a bunch of equivalences. Then those equivalences just forms the spatial sense of your mind. Okay, and you may form some sensory motor contingencies or schema or whatever you name it. You'll find that when your body is in a certain position and you have a certain action signal, then it will move. It will change into another positional representation. Then you can learn this kind of knowledge so that you know how to move in this subjective space. Okay, so this is also a example so that it can provide you some intuition. Yeah, so temporarily we can differentiate two different spaces, external space and internal space. So the external space is the space outside the system. It's what you just suppose you are the god of the world, and you know there is a space in the environment. You are the god, but the system doesn't know the space. It has no notion of the space. Okay. You can see the system here. There's a stick, but it can stretch and also rotate, and also there is a sensor in the end of the stick. So when this agent moves to somewhere, it feels something, and moves to another where, feels another thing. And it found that the feeling from B to B prime and the feeling from A to A prime are the same. They found that it can perceive the same triangle. You can see here is a red triangle here and a purple triangle here. So if the system feels the red triangle, it moves from A to A prime, the two different vertices. But after the triangle moves to another place, then the system can still feel that they are the same thing because the feeling from B to B prime is equivalent to the feeling from A to A prime, so that they are the same. So it knows that they are the same shape or the same triangle. Okay, and so now, previously I said we are the God, so that we know there's an objective space. But now that's removed that assumption. We're not the God. We are also a agent. We are similar to the machine. We don't have a notion of the space. Then how can we know that there is a 3D space there? We do the same thing as the agent, as the machine, right? We also try to perceive the world through our sensory motor experience. In this sense, we don't have to assume an objective space. We just assume we have some mechanisms that can form the equivalence of the equivalence of changes. The equivalence of changes. What changes? The changes of positional representations, right? Okay, so now I want to raise an open challenge. It's how to learn a space. There are some work which can learn space with some idealized assumptions, but for AGI systems, there should be some constraints. Firstly, we don't have sufficient memory, and we don't have sufficient processing time. Both of them are insufficient, and the system cannot be passive. It's not like a neural network which passively accept some images and use backpropagation to clarify them into some categories. We don't do that. We hope the systems can move autonomously, and finally we hope the system should be fully interpretable, because we want to understand how our mind works. So we need a normative theory, and the whole system should be interpretable, so that we can exactly know how it works, and then we can verify the knowledge of how our mind works. Okay, so maybe I should skip this. In our paper, we have some comparisons with other theories, for example, David Marr's theory of vision and so on. And this is the source code to produce the result in this presentation. And thank you for listening. Yeah. And any questions?
Well, I have only one question. So,
Yeah.
I'm trying to understand how do you define or distinguish space parameters
Distinguish what?
and just parameters. Space parameters, spatial parameters,
Okay.
and another set of parameters. Because having in some parametric space, you can just play with some parameters and identify special parameters, right? Spatial parameters. So what is your approach? Do you like define in advance? This is about space. This is about not space, or you can identify space parameters or special parameters in the like during the work.
Yeah, I see. Good question. So since we haven't implemented a complete AI system which can learn spatial structures, so my answer is about the future plan. So I think this is a good point that we can distinguish spatial parameters or spatial attributes from other attributes. For example, the spatial attributes comes from our body feeling. Like we can feel the position of our body, like with hands raised up or put down. They have different body feelings, right? So these feelings can be marked as spatial parameters. So we can have some spatial learning mechanisms on this, yeah. So we have some special mechanisms to learn a spatial structure. But
you mentioned that you have like visual input.
yeah,
You change your position somehow,
yeah,
but you change not like your body internal parameters.
yeah. That's also a good
But
question.
special field is changing somehow, right?
Yeah.
Or
So
speed.
mhm.
So it's not like
Do you want this?
No, just that people hear you from the laptop if you stand there.
Stand here.
Just stand there.
Okay. Could you repeat your question? Sorry.
so my question is, you said that your special parameters relates only your internal body
Yeah.
feeling.
Yeah.
I claim that in some cases, like you change
Vision,
the
right?
speed of moving, your visual field is changing.
Yeah.
Is it special or not?
So for vision, so you can control your eyeball. You can see different directions, right? That's kind of a movement or body feeling. And you have a retina, which it's like a a tessellation of neurons, and you can have give each neuron a relative position, so you can use the same mechanism to handle this. And for the speed issue, frankly speaking, I didn't consider this much before, but I will consider it later, and maybe we can have some discussions.
So I got your point, but my understanding, just to share my opinion.
Yeah.
So in some cases, you have special related input without your ability to kind of do active inference. If you are falling down, so you see the changing
Oh,
of your
yes.
special field, but you
Yes.
do nothing.
Yes. So in that case, so using this theory, in that case, the system cannot really know the space, cannot really understand the space. Yeah. And I think there's some psychological or cognitive experiments. Say if you don't make a person to move around actively, you just move it. It can move passively. It cannot learn the knowledge about space or cannot really understand the space. I remember there are some experiments support this implication, but we don't need to care about that. Just using this theory, then that would be not working. Yeah.
Okay, I see it. Just to probably you know that Francois Chalet has a paper measurement, something like some measurement of intelligence, and he claimed that there are some prior knowledge.
Yeah.
And special knowledge is one of them. So probably it's worth to like look at knowledge from this perspective.
Yes. So that's the issue of different selection. So what do you think is innate and what do you think is acquired? Or what do you think is a priori, or what do you think what is experience? And different people have different selection. So maybe my selection is different from Francois Chalet. He thinks he may follow Kant's assumption that space is a priori, but I prefer the sensory motor account. But yeah.
Okay. Thank you.
Okay, so theoretically, we have another two speakers. One is David Ireland, but unfortunately, David is unable to be with us today, and he will prepare a recorded presentation, and we will put it on our workshop website. And another speaker is Jeffrey Freeman. His topic is about domain agnostic evaluation. And yeah, so I think there's still some issues of traveling for him. So we will request him to like maybe he will record a video and we will put it on the website too. Yeah. So and so I think we can have some general discussion because there are some friends online, and maybe this is a opportunity to respond to the public. And I will ask Dr. Pei Wang to respond to the issues raised by. Maybe I should go back. Stop share. Yeah. So there were two issues raised by some friends online. The first one is hasn't NARS admitted defeat to LLMs? And another is that what's the relation between NARS and LLM? Can they be converted to each other? For example, you can explain LLM using NARS, or you can explain NARS using large language model. So I'm wondering if Dr. Pei Wan has some response to those issues.
Okay, both are big topics. For the first question, we do have a clear answer, which is no. Simply because it's not because we do not acknowledge the great success of large language model, but because we are not working on the same thing. For that, I have written several articles in the past decades, which is based on analyze about different understanding of intelligence. So for NARS, we have already mentioned what we want to do is we want to build an adaptive system which work with insufficient knowledge and resource, which is my understanding of intelligence, which is also shared by many other people in the team, which actually implies what? Which implies that NARS, even after it's fully implemented according to the design and actually turn out to satisfy our expectation, it will not be like a large language model because it will not, it will behave according to its own experience, which is not necessarily the same as human experience. So we never try to pass a Turing test in the first place. And we do have a lot of argument to say why this is also a valid understanding of intelligence, even though they can understand it in some other way, just like many concepts, different people use it in different way. Here, very often it's not which is right, which is wrong, and also it's not because the one is more common, more popular, is more accurate or correct. It's just because they lead to different things. Okay, there's some overlap. No. So even though large language model achieve a lot, we don't think they do better. Actually, if you follow our discussion, you will see that they are not really working on the problem where they are struggling with. They do not give a solution for our problem. Okay? So there are two different things. Just for historical reasons, they both are called AI, and now they're both referred to as AGI by different people for some reason, but they're not the same. The second question, yes, we completely agree that we should combine the two, technology and in a certain way. And now the real question is in which way, which I think Tang Rui has already said a lot on how to combine, or the approach we have tried to combine large language model and the NARS, and each of them uses strengths and do something together. And also, if Patrick is still in the room, he can also tell us a lot more about that because he was the first one in the NARS team to actually try to do that with some success. This is still a big topic, a long way to go, but I don't want to go into too much technique. It's simply because Patrick and Tang Rui know more than I do on that topic. So if anyone still want to know, and maybe they can give an answer or more explanation. So that's what I want to say on those two topics.
Okay. Yeah, I think that makes sense. And finally, so are there any other general questions? And any questions are welcome.
So probably one question.
Yeah, sure. I'm here.
So hello. My question is about dual implementation of NARS. So my understanding is that like conscious and automatic levels are corresponding to like Daniel Kahneman system 1 and system 2. So is it so? If yes, how in NARS the conscious knowledge or conscious actions could be converted to like automatic ones? Is it possible or not?
Oh, I will try to answer it. I think this is related to my presentation at the beginning of the workshop. Even though it go deeper, so I will add a few more things. First, which I didn't mention, but is described in my previous publication. I don't really take consciousness as a necessary condition for an intelligent system. But I do take it as a good feature or probably a necessary feature for advanced form of intelligent system. That is why in the design of NARS, this consciousness actually was introduced very late at layer 9. So it's kind of like, I go back again to my definition of intelligence. From the very beginning, NARS is try to be adaptive to the environment, meaning that it will summarize its experience into knowledge. But here, the experience from the very beginning is most about the external environment. So all the previous implementation of NARS basically know nothing about itself or very little about itself. But it will know something more and more about the environment. But when we are moving, again, like many people will say, so intelligence, according to my definition, is still a matter of degree. So there are some low intelligence system, there are some high intelligence system. So for the low intelligence system, it doesn't need to know itself. It only need to know the environment. But if you want to be really highly adaptive, it is very actually become more and more than necessary for you to know your own working process to a certain degree. Again, that's you never completely know yourself, just like you never completely know your environment. So that is why I believe consciousness is related to high level of intelligence, but not necessarily in all forms of intelligence. So that's I think answered the first question. Probably the second question about system 1, system 2, which I didn't mention those two words in my presentation, but yes, it is related. Actually, in psychology literature, there are several pairs of categories. I mentioned two of them. One is the controlled process and automatic process. Another pair is consciousness and unconsciousness. And then the third pair is about system one and system two. These three pairs are kind of like intuitively correlated to each other, but they're not exactly about the same thing. So you can say conscious is related to controlled, and unconscious is related to automatic. And also system one, system two is also correspond to this two. But there's, so in this sense, yes. In the previous version of NARS, the inference control is purely automatic. The system does not have much control. It's basically attention will just flow to things that which have a high priority, relatively speaking. And the priority, on the other hand, is determined by several factors which are calculated automatically. But now we are trying to add some control by the system itself into its own thinking process, even though in a limited form. So in this sense, I also mentioned in my slides, you can say that there is a dual process in a system. There is a system one, system two. But on the other hand, there is one interpretation about this terminology I don't like too much. That is, some people assume this system two and system one are separate mechanism. To me, they're only relatively separate. Yeah, since in NARS and also in the design, I didn't stress that. You can see that there is continuous degree in a sense. So to what extent something is conscious or subconscious, sometimes it's not very clear. There are things on the boundary. So to me, it's also something, it's kind of like in the boundary between system one and system two. Especially, I don't believe there are two separate mechanisms. You can study them separately, then somehow you integrate them into an AGI system. I don't completely buy that, even though the difference clearly is there. So that's my attitude toward this topic.
Okay, thank you for your answer. So I'm not claiming that I support this strong separate to two parts. I agree that this is more continuous separation between consciousness or self-aware thinking and automatic actions. But my feeling, if we consider robotics, they rely on control loops, which are completely automatic without any extra knowledge from outside. So they implement only control mechanism according to differential equation or something, dynamic model. So, and I'm wondering, is it kind of possible way to generate some control feedback based loops for control the hardware in this system, maybe in the future, because time constraints are quite important in real time, especially.
I completely agree. I think it's possible. Actually, in a sense, that's what today's talk is about. Our previous work on robotics, especially mostly done by Patrick, who is also here at the conference, is to use a control mechanism generated by the inference system NARS. And if we add this self-control functionality into NARS, which directly means that we can use that to control a robot. So the robot not only it can follow an automatic built-in routine to do things, it can also do reasoning in novel situations, especially in novel situations, and even ask itself, what I have done to lead me into this situation, how can I get out of it? by changing some of the habit I have formed so far. We are not there yet, but that's exactly what we want to address with this self-control functionality, which will also apply to robotic implementation of NARS.
Okay, thank you.
I guess there are no other questions. General questions about NARS? No? Okay. And no questions online? Okay, so yeah, so then I think we can end this workshop, and I'd like to extend a heartfelt thank you to all our speakers as well as the audience. And we thank the and also appreciate our sponsor Clever Libre for their support, and also the audience here in Reykjavik and also online for your engagement and curiosity. So thank you and enjoy the rest of conference. And that ends the workshop.